Hi, welcome to Concept Based. I'm John Hepworth, and this is a tricky question. It's going to cover a few concepts for us today. It's for Year 11 Extension. We're in the polynomials section of your syllabus, and this is looking at remainder and factor theorem. This is looking at definitely a tricky application of the remainder theorem, as it brings about a little bit of understanding that you have to have about the remainder when calculating the remainders, that it then allows you to go on and do additional algebra in this question to solve it. I think this is possibly the most tricky question for remainder theorem for students. It doesn't follow the same sort of pattern as other questions do, and a lot of the other questions can be quite procedural, whereas this one definitely requires in-depth understanding and a recognition right from the beginning that there's something that's different. So what is that? Well, let's see if we can find it. So first of all, the question: a polynomial p of x is divided by x minus 1, x plus 2. The remainders when divided by x minus 1 and x plus 2, so individually, are 5 and negative 7 respectively. Find the remainder when p of x is divided by x minus 1, x plus 2. Okay, so two things essentially are going to happen here. We're going to divide a polynomial by x minus 1 and x plus 2. And then we're going to divide a polynomial by x minus 1, x plus 2. Okay, so that's fine. And we're given some remainders for what happens. So let's just look at the general understanding of, first of all, what happens when we divide by a linear factor. So we know that we have this general form of our polynomial, which is some divisor results in some quotient plus some remainder polynomial. And we need to know that all the time. If you don't know that, then definitely revise the content that you've been doing, because we have to start from somewhere, and this is definitely the place to start from. But in this situation, we're given some of this information. We're given that when we are dividing by x minus 1, I'm just going to write q1 of x because there's going to be another q of x shortly. We're told that the remainder is 5. Now we need to understand that that means r of x is straight up just 5 in this situation. And why is that? So the idea is that if we put 1 into this function, then we would replace this x with a 1, and 1 minus 1 would be 0. And therefore, this whole section would disappear because 0 times q of x is 0. So therefore, we would only be left with the remainder, and we're told the remainder is 5. So therefore, the remainder polynomial, when we do this division, hooray, pen, when we do this division, must be 5. Now, I can still write p of x just like this. So if x minus 1 is a factor, or is the divisor, we're going to get some quotient, which we don't know and will never know, plus 5. And then we've also got the other situation. So we've got the situation where p of x equals, we could use the other linear factor or divisor, and that was x plus 2, and that would create a different q of x. I'm going to call that q2 of x. And we're told that that has a remainder of negative 7. Now, we can't actually go and just use these to solve each other, and that's often where students will go wrong. They're like, oh, this is just simultaneous equations. I can just let p of x equal itself, and then I can just rearrange things, and I don't know, q1 of x and q2 of x will just appear or something, or I can make something a subject and move on. And that's a path of no return that doesn't get you anywhere, and that's definitely not something that I would recommend to do as a step in this situation. What we really need to recognize here is what is being asked of us in the final question. And it's being asked to create a p of x. Better start a bit further to the left because I've got a couple more divisors here, or a big divisor. X minus 1, x plus 2. I'm just going to write q3 of x because there's now another quotient that we're going to end up with, is going to end up with some r of x. Now, this r of x is what's interesting. Now, if you know what I'm about to say, then excellent. You're across polynomials and you're across the idea of remainder theorem, and you understand what is the details of doing division, polynomial division. But if you're not sure what I'm going to say about r of x right now, then this is definitely something that I would add to your learning log around this content, this topic, because it's just something that can be easily forgotten or missed. And when you revise this topic and you go, that's right, r of x, blah, 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 is a great thing to remember. So r of x, when you divide a polynomial by degree anything, let's say a degree n, then the remainder can be a polynomial degree n minus 1. What does that mean? What are you talking about there, Mr. Hepworth? You just spoke about n's. What are you doing? I'm just saying that if we have some general polynomial and so on, and we divide this by, say, x minus alpha, what will happen is we'll either have the factor go in perfectly, we'll get some other polynomial, I'm just going to call this a2 x to the n minus 1. It'll be 1 degree smaller because the x has gone in. We'll just say b2 x to the n minus 2, and so on. But when we come down here and we take everything away, we're going to end up with our r of x down here. Now, hopefully you've noticed that while you're doing all your remainder theorems and factor theorems, this r of x, when you put a linear, right, a linear factor goes in, you get either nothing, because it is a factor, or if it isn't a factor, you get a number. You get some sort of constant, 5, -7, like back up in here in the question. We put it in and we just got this remainder that was just a number, a constant. But if you go and you divide this by something a little bit more chunky than that, this is a different b. I don't know what b I'm up to. B3, C1's fine, but I'll call it C3. So now if we go and divide ax to the n by this x squared, obviously the resultant polynomial, the quotient that we're going to end up with, is going to be 2 degrees smaller, plus b2 of x to the n minus 3, and so on. We get some quotient. But what I care about is this r of x down here. What happens when we get to the end of this, and when do we stop? So the idea is that we can't keep dividing if the resultant polynomial that we end up with is a lower degree than the divisor. What do I mean by that? So we go and we do all of these lines of work and we subtract away and we get down to something that looks like this. It would be some sort of x minus, let's just call this C4, x minus C4. So the degree of this polynomial down here is a degree 1, but the divisor is a degree 2. And we can't keep dividing into that remainder if the degree in the divisor is larger than that in the remainder, because it would just result in a negative index. And by definition, a polynomial won't have a negative index. And by definition, r of x is a polynomial. So therefore, we can't continue to do this division down here and start getting x to the -1 or anything like that. So we have to stop. We have to stop when we get some sort of linear factor. I probably could have put an a out here. What a am I up to? 17? Let's just call it a17. Okay, that's excessive. But we get some sort of linear factor and we have to stop. A linear factor when we divide it by something to the degree 2. Okay, why did we go off down this side path here, Mr. Hepworth? What are you talking about? Why do we care? We care because look what we're dividing by. We're dividing by 2 linear factors. Now, if we expanded x minus 1, x plus 2, we would get a polynomial degree 2. It'd be x squared plus something, minus 2. So therefore, our remainder polynomial, this one over here, is going to end up being some sort of linear function, a degree 1 polynomial. So we're not going to write r of x, we're going to write a degree 1 polynomial, but the degree 1 polynomial can have a leading coefficient and can have a constant term. So we end up with ax plus b. If you make it to this part of this question without looking up anything, without any support, you're probably going to make it. You're probably going to get the answer out. You've come far enough. So this is the trick. And we love it as mathematics teachers writing questions, not that are tricky, but have got you know, some deep understanding, some conceptual understanding that must be demonstrated by the student to make any progress on the question. So yeah, having a question that results in you having to do this ax plus b is very likely to be in some sort of polynomials test that you're given in an extension course. Okay, so what now? We've got this big expression with this divisor that's huge and this q3 of x. We're not getting anywhere, but we're getting very close, because now if we go and put 1 into our polynomial, if we put what we had up the top there that we know about, well, now look what we get. 1 minus 1. 1 minus 1 is 0, and that therefore is going to wipe out anything in this section. 0 times anything is gone, but we now need to put a 1 in for our x here, so we end up with a plus b. But we know that p of 1 from back up here had a remainder of 5, so this actually equals 5. So we know that a plus b equals 5. We do the same thing for p of negative 2, which is going to cancel out the whole middle bit again. And then we're just going to have plus, we're now putting negative 2 in where x is, negative 2a plus b. And we're told earlier in the question that this is equal to negative 7. And we have landed in the world of simultaneous equations inside of our polynomials, where we're doing remainder theorem and even factor theorem, I suppose you could consider here. So now we end up with this. We end up with a plus b equals 5, and we end up with negative 2a plus b equals negative 7. Now I could just go ahead and solve this, but I want to keep reinforcing to you that it's really important that you understand how to solve simultaneous equations by any method, by elimination or by substitution. I know you had a favorite way in year 10, and I know that you wanted to stick to that way in every situation in extension 1, but stop doing that. I don't know what analogy to make here. I was thinking of one this morning on the way to work, and I thought, imagine an MMA fighter who's really good at stand-up, but has no jiu-jitsu on the ground. What should they work on? Obviously, they need to work on their jiu-jitsu on the ground, because they're not an all-round athlete if they don't have that area of a skill. So in this situation here, if we don't know how to do the elimination method and we only know how to do the substitution method, we should work on our elimination method. We want to have both methods available to us so we can just choose at any time whichever one's better. Because if you look at these two, the elimination method is just an immediate way to the solution. So if this was an equation 1 and this was an equation 2, then we could just do equation 1 minus equation 2, and we're going to get a minus negative 2a, so we're going to end up with 3a. b minus b is gone, which is why elimination method was so good, and 5 minus negative 7 is 5 plus 7, which is 12, and a is going to equal 4, and I'm going to put that straight back up into this equation, and I can see that b is equal to 1. So therefore, don't forget to answer the question being, find the remainder when it is divided by this. So we now know that the remainder, when the polynomial is divided by that expression or that polynomial, we get r of x is equal to 4x plus 1. And we have arrived at the solution. So, as was always with mathematics, if somebody does something for you, maybe you go to Copilot or ChatGPT and you say, hey, solve this question for me, and you just chuck it into AI and it gives you an answer, a brilliant answer. AI is great at giving you answers, and it just pumped this solution out for you. You'd be like, oh yeah, I know that's what I should do. But it's really important that you do questions blind. You find where you get stuck. And the critical point in this one is right here, of understanding that in that line, if you did not notice that there should be a linear remainder, then you're never getting to the solution in this question. So add it to your learning log, do practice questions like this somewhat regularly so that you're reminding yourself about the size of the degree of the polynomial of that remainder. Again, if you're looking for any sort of tutoring tips like these, please feel free to contact me, info@concept-base.com.au. I'd love to work with you.